Swayam Prabha. Digital India. Educated India.
Namaskar. So, in this week we discussed few important properties of the network. We started with the linearity property of the circuit, where we discussed what is homogeneity and additivity, and then we proceeded towards the superposition theorem, and then we discussed the other concepts like source transformation and the duality, and then in the last class we started our Thevenin's theorem. So, in the last class we basically discussed the Thevenin theorem aspect when the source is non-dependent source. So, that can be like voltage or current, both were independent sources. So, in this class we will continue our discussion on the Thevenin's theorem, but we will discuss more about the dependent sources, that may be the voltage or current. So, now let us start. First let us recap what we discussed in the last class. We discussed Thevenin's theorem, and we discussed that the linear two terminal circuit can be replaced by an equivalent circuit consisting of the voltage source Vth in series with a resistor Rth, where Vth is an open circuit voltage at the terminals and Rth is the equivalent resistance at the terminals when the independent sources are turned off. So, when we calculate Rth, we make the independent sources turned off. That means that voltage source, independent voltage source would be short circuited and independent current source will be open circuited. So, what we discussed, that if we have a fairly large circuit and we want to study the load connected across two terminals, then the circuit which is left of the nodes A and B can be approximated, rather can be equaled with the voltage and resistances shown in the figure. So, voltage would be considered as a Thevenin voltage and resistance would be considered as Thevenin resistance, and we will see that the Vi characteristic across terminal A and B will be same in both of the cases. So, that means that both of the circuits are equivalent because their Vi characteristics are same. So, this is what we discussed in the last class, and then we stabilized that Thevenin voltage is nothing but open circuit voltage across the linear two terminal circuit, and Rth is nothing but the input resistance at the terminal when independent sources are turned off. So, if you look from this side into the terminal A and B, the equivalent resistance which you will see from here is nothing but the Thevenin resistance. Now, we also discussed that for calculation of Thevenin resistance we need to consider two cases. What was the first case? In first case the network has no dependent sources and we turn off all the independent sources. Turn off means, as we just discussed, that voltage source would be short circuited and current source will be open circuited, and then Rth is the input resistance of the network looking between the terminals A and B, that was shown in the previous figure. Now, in this session we will discuss more about the case 2. What is case 2? That in case the network has dependent sources, we cannot turn off the dependent source because it is depending upon some circuit variable. So, we will keep dependent source connected with the circuit, while we can turn off all the independent sources only. And then since the dependent source cannot be turned off because they are controlled by the circuit variables, we will keep them in the circuit and we will apply voltage, that is V naught, at the terminal A B and determine the current I naught. So, what does it mean? If you have circuit with all independent sources set equal to 0 and the keeping all the dependent sources connected with the network, the terminal A and B would be supplied with voltage V naught, which will supply some current I naught. So, in that case, if you solve this circuit with the help of either Kirchhoff voltage law or Kirchhoff current law, you will be able to find out the value of Thevenin resistance, which would be nothing but V naught divided by I naught. So, when you have dependent source available in the circuit which you cannot remove, you will first remove all the independent sources and then apply voltage V naught and try to measure the current I naught, and accordingly you can find out the value of Thevenin resistance. Now, alternatively RTH can also be evaluated by inserting a current source. So, instead of voltage source, if you apply current source, you will measure the voltage across these two terminals, and when you measure, you will get again the value of RTH as V naught upon I naught. So, in both of the cases you can use either of them and you will get eventually the same result. So, what the process we need to follow when the circuit contains a dependent source? We have to find RTH, that is Thevenin resistance, we have to set the independent sources equal to 0 and leave the dependent sources connected. Now, since the network has dependent sources, we have to excite the network from outside with the help of either voltage V naught or maybe the current source I naught, which would be connected to the terminals. Generally, we set V naught equal to 1 because it will be easier for our calculation, and since the circuit is linear, that means that we follow the homogeneity concept. So, whether it is 1 volt or 10 volt, the response of the circuit will be scaled up accordingly, and being a linear circuit, it is very easy for us to apply any voltage which we want across the terminal, but the easiest is 1 volt because it makes calculations easier. Now, next is that we have to find out the value I naught because we have added voltage V naught across the circuit. So, I naught we can calculate, which would be flowing through the terminals with the help of either KVL or KCL, and then we obtain the value of Thevenin resistance, that would be nothing but V naught upon I naught. V naught is in this case 1, so it will become 1 upon I naught, or we may insert 1 ampere current source. So, this will give you the RTH value as V naught upon 1 because 1 is the value of current source. Now, let us understand this concept of how to solve the circuit when we have the dependent source with the help of one example. Now, let us see this particular circuit. There you will see we have one independent current source of 5 ampere value. Additionally, we have one voltage source which is dependent voltage source, and the value of voltage is depending upon the voltage across 4 ohm resistance. Now, what we have to do? We have to find the Thevenin equivalent to the left of the terminal A B. So, we have to find out the Thevenin equivalent, which would be the equivalent of the complete circuit. Now, let us solve it. What we have to do first? First we have to solve for RTH, that is Thevenin resistance. In that case what we can do? We can remove all the independent sources. So, in this case this is the independent source, and since this is a current source, you can make it open circuited. So, the resultant circuit would be like this, and what we need to do is that we need to add one voltage source V naught, that is equal to 1 volt, which would be connected across the terminals A and B, and then solve the circuit. So, here we have made the current source as open circuit, which was connected across 4 ohm resistance, and additionally we have added one voltage source across terminal A B, that is V naught is equal to 1 V. So, the updated circuit is as shown in the figure. Then you will see that how you will solve. You can use mesh analysis, which we discussed earlier. So, here we have 3 meshes connected. So, we will have 3 mesh currents like I1, I2 and I3. Now, what we have to do? We have to solve the circuit using mesh analysis. So, what would be the value of the mesh equation in case of loop 1? So, this is loop 1. So, when you solve, since it is going from minus to plus across the dependent voltage source, it will become minus 2 Vx plus 2 times I1 minus I2, because it is I1 is going in this direction while I2 is in this direction. So, this will become 2 times I1 minus I2 and finally equal to 0. When you simplify, you will get Vx is nothing but I1 minus I2. Now, if you see this particular mesh, you will come to know the voltage drop across 4 ohm resistance is nothing but 4 ohm into current I2. Now, since the direction of current is opposite of the polarity of the voltage, so what will happen? You can simply say Vx is nothing but minus of 4 I2. Now, you know that Vx is equal to I1 minus I2. So, in that case you can simplify and you will get the value of I1 as minus of 3 I2. Next, what we have to do? We have to apply KVL for loop 2 and 3. So, for loop 2, if you apply KVL, what will happen? The I2 is going in this direction, so it will be 4 I2 plus 2 times I2 minus I1, because I2 in this direction, I1 in opposite direction, you will have 2 times I2 minus I1. Similarly, for 6 ohm also, I2 is in this direction and I3 is in opposite direction. So, you will get 6 times I2 minus I3 equal to 0. So, this you will get from loop 2. For loop 3, what you will get? 6 ohm multiplied by I3 minus I2 plus 2 times of I3 plus 1, because this is the external voltage source we applied across AB, equal to 0. Now, if you see this equation, if you simplify, that is 6 I3 minus 6 I2 plus 2 I3 is equal to minus 1. So, if you simplify, this will become 8 I3 minus 6 I2 is equal to minus 1. So, you will get 8 I3 minus 6 I2 is equal to minus 1. Now, if you simplify this equation, what you will get? You get 4 I2 plus 2 I2 and then minus of I1. So, what you will do? You will put the value of I1 here, and what you will get? The equation you can simplify as 4 I2 plus 2 times, since you put the value of I1 as minus 3 I2, this will become 4 I2. So, this will become finally 8 I2 plus 6 I2 minus 6 I3 equal to 0. So, when you will simplify, how much you will get? You will get the 18 of I2 minus 6 I3. So, you will say like minus of 6 I3 plus 18 I2 is equal to 0. Now, you have these two equations. You can simply solve it because you have two equations and two unknowns. So, when you will solve, you will get the value of current I3 as minus 1 by 6 ampere. Now, as we know that I2 is equal to minus I3, if you see this circuit, I0 is in the opposite direction of I3. So, we can simply say I0 is minus of I3, that is nothing but 1 by 6 ampere. So, what you will get for RTH, since we know that RTH is nothing but V0 upon I0, V0 we have as 1 volt which we have applied, and I0 we have 1 by 6 ampere. So, 1 by 6. So, finally, you will get the value of RTH as 6 ohm. Now, what next we have to do? We have to find out the VOC, because RTH we have already found. For finding out the value of VOC, what we have to do? We have to find out the voltage across terminal A and B. So, we will add the 5 ampere independent current source again in the circuit, and then we will solve. So, again we have 3 meshes created in the circuit, that is I1, I2 and I3. We will write the mesh equation for all 3 meshes. So, if you see this one, you will simply get I1 is nothing but 5 ampere, because this is the independent current source connected to this. For next this mesh, what you will get? So, this you will get basically the value as I2 is going in this direction. So, you will get 4 times, this is I2, this is I1. So, 4 times I2 minus I1 plus 2 times of I2 minus I3 plus 6 times of I2 equal to 0. So, the simplified of version of this equation would be 12 I2 minus 4 I1 minus 2 I3 is equal to 0. Now, let us talk about the mesh number 3. What you will get? You will get minus of 2 Vx plus 2 times of I3 minus I2 equal to 0. So, what you will get? Vx is nothing but I3 minus I2. Now, we know that what is the value of I1? I1 is nothing but 5 ampere. You can simply put the value of I1 in this equation, and you know that we have these two equations, and also we know from the dependency, because this is the constraint value, that is variable Vx is nothing but 4 times I1 minus I2. So, when we solve these equations by putting the value of 4 of I1 minus I2 in this, you will simply get, so that is 4 times I1 minus 4 I2 is equal to I3 minus I2. I1 you know that is 5. So, this will simply become I3 plus, that will go here, then I3 plus 3 I2 is equal to 20. So, this you get another equation which is only in terms of I3 and I2. You will put the value of I1 here, you will get 12 of I2 minus 2 I3 is equal to 20. Now, you have these two equations where only unknowns are I2 and I3. So, you can simply solve, and finally, you get the value of I2 as 10 by 3 ampere. Now, you have got the value of I2, what you will get VTH. So, if you see this circuit, VOC is applied across terminal A and B. Since no current is flowing in this particular 2 ohm resistance, this VOC would be applied across the 6 ohm resistance. So, the voltage drop across 6 ohm resistance would be the value of Thevenin voltage. So, we get VTH is nothing but VOC equal to 6 times I2, nothing but 20 volt. So, now we have got VTH, we have got RTH. So, our Thevenin equivalent circuit will look like this, where 20 volt the voltage source would be in series with 6 ohm resistance. So, now let us see another example. In this circuit, if you see the circuit, we want to find out the Thevenin equivalent, but in this particular circuit we do not have any independent voltage or current source. So, this circuit would have only dependent source. So, here in this case we have the current source which is dependent. So, what we have to do? We just see that this circuit contains 2 ohm resistance in parallel with 4 ohm resistance. So, these two are in parallel and they in turn are in parallel with the dependent current source. Now, first thing which we have to consider is that since we do not have any independent source in the circuit, we must excite the circuit externally. What does it mean? Then we have to apply either the voltage or the current source across the A and B terminals, so that we can excite this circuit from outside to find out the value of Thevenin equivalent. Now, another thing which we have to consider is that since we do not have any independent source, we need not to have the value for Thevenin voltage. Why? Because if you see this figure, the value of this particular current source is depending upon the current flowing through 2 ohm resistance. So, until unless we have any external source, you cannot energize this particular circuit. That means that if you are having the A and B terminal as open circuited and you want to find out the open circuit voltage across terminal A and B, this will always be 0, because there is no independent source to supply power to the circuit. So, in that way you can simply say that we do not have any, we need not to calculate VTH for this type of source. So, what is left is that we need to find out the value of only Thevenin resistance. So, next the simple approach is either you apply 1 volt voltage source or 1 ampere current source. So, now let us apply one current source and try to solve it. Now, what we will do? We will see that this particular circuit has one node, the voltage across this particular circuit A B would be nothing but the voltage across both of the resistances also, because all those elements are in parallel. So, what we will do? We will solve it with the help of nodal equation, because it is easier to apply Kirchhoff current law in this particular circuit. So, let us try to apply nodal equation while putting the value of I naught as 1 ampere. Now, if you see this node, whether this is A or this node or this node, all are at same potential. So, eventually this will be considered as a single node. So, at this node if you apply the Kirchhoff current law, first thing is that at this particular node current going outside is 2 of I x, another current going outside is V naught by 4, another current going outside of this node is V naught by 2, and then the current going inside is the current I naught, right, because the direction of current I naught is in this direction. So, this will become minus, or you can simply say this all equal to 1. Now, if you solve it, what you will get? You will get the equation in terms of V naught and I x. Now, the problem would be that since we have only one equation and we have two variables, means we need at least one more equation to solve this circuit. So, from where we will get the second equation? The second equation we will get from the constraint equation, that is the constraint in this case is current I x, which is defining the value of dependent current source, that is 2 I x. Now, if you see the value of I x is nothing but minus of V naught by 2, because the direction of I x is opposite to natural flow of current if voltage V naught is having higher potential than the reference. So, in this way this will become minus of V naught by 2. So, what we can do? We can simply put the value of V naught in this equation. So, finally, when you put this value here, you will have only V naught as an unknown in this equation. So, you can simply solve it by putting the value of I x, that is minus 2 minus V naught by 2, and when you solve it you will get the value of V naught, which is equal to minus of 4 V. Now, since V naught is 1 into RTH, because I naught in this case is 1 ampere, simply the value of Thevenin resistance would be minus of 4 ohm. Now, the negative value of resistance will tell us that according to the passive sign convention, the circuit is supplying power. Since the resistor cannot supply power, who supplies this power? The dependent source, which is connected to the network. Now, in this example we have seen how a dependent source and resistor could be used to simulate the negative resistance. So, this property is very important. Sometimes you need to insert negative resistance in the circuit, and you can realize with the help of these type of circuits. Now, if you solve this problem using different approach, whether the same solution would be obtained or not, let us see. So, now suppose we have load of 9 ohm resistance and 10 ohm voltage connected across the terminal. So, what happens when you have a load of the 9 ohm in series with 10 volt source, how you will solve this circuit? Suppose you are not following the Thevenin theorem and you want to analyze this circuit, what you will do? You will simply see the circuit, that is, if you see this particular segment, you will see that one current source is in parallel with one 4 ohm resistance, right. So, what you can do? You can apply source transformation and you can solve it by converting the combination of current source in parallel with 4 ohm resistance with the voltage source in series with 4 ohm resistance, that is the source transformation technique which we studied earlier. So, what will happen in this case? The value of the voltage source, and that is definitely would be the dependent voltage source, because this is the dependent current source. So, the value of voltage source would become 2 into 4, that is 8 I x, and the direction of plus sign, the polarity would be plus, would be in the direction of flow of the current. So, that is why the below sign is plus, up sign is minus, and then in series with 1 4 ohm resistance. So, this particular segment is now converted into voltage source in series with 4 ohm resistance. Then you add 2 ohm resistance, that is the part of the circuit in parallel again, and this is the load component which you have connected at terminal A B. So, the updated circuit would be looking like this. Here we have two meshes. So, what we have to do? We have to write the mesh equations for both of them. So, these would be the two mesh equations for these two meshes, plus we will have another constant for I x, that is nothing but I 2 minus I 1. Now, if you use these three equations and solve it, you will get I 1 is equal to 3 I 2, and using KVL in loop 2, you will simply get I 2 is nothing but minus 10 divided by 5, because you solve it with the help of the circuit and you get the value of current I 2, because I 1 is nothing but 3 I 2, and you write the loop equation for this. This is what you have used in case of mesh 2. Put the value of I 1 here, solve it, you will get I 2 is nothing but minus 2 ampere. Now, this is what you got when you did not apply Thevenin theorem to solve this particular circuit. Now, you know that we have calculated the Thevenin resistance across these two terminals, while there was no Thevenin voltage. So, if you use that concept of Thevenin theorem which we discussed, we will have only 1 minus 4 ohm resistance as part of the Thevenin resistance with no Thevenin voltage. So, the left side of this, which was our original circuit, can be replaced by only the 4 ohm, that is minus 4 ohm resistance, that is Thevenin resistance connected across terminal A and B. So, we have now very simple circuit when we consider the Thevenin theorem, and we get the equivalent resistance of this particular loop as 5 ohm plus 10 volt voltage source is connected. When you apply again the KVL in this particular circuit, you will get again current I as minus 2 ampere. So, if you compare these two methods where you analyze the circuit with the help of source transformation, and then you applied the mesh analysis method to find out the value of current I 2. Here we used the Thevenin theorem and simplified the circuit very quickly as compared to the method where we were using the only the dependent voltage and current source when we connect them, and how to create the Thevenin equivalent in that case, and how to solve the circuit when we have dependent sources connected. So, with this we close this week sessions where we studied various key concepts of the circuit. We studied superposition as well as Thevenin's theorem. So, next week we will start with another theorem which is called as Norton's theorem. Thank you.